Hello and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. In this module, we will discuss wave propagation in anisotropic medium. In the previous modules, we have assumed that the material properties of permittivity and permeability are constants, therefore we just give a number to them. So it could be the total permittivity or total permeability, epsilon or mu. Epsilon was given by epsilon r into epsilon naught, where epsilon naught was the free space permittivity and epsilon r was a relative dielectric permittivity. And whether your incoming light was polarized along x axis, y axis, whether it was circular polarized, it did not matter because the properties did not depend on the direction of light propagation. In other words, the value of epsilon r was the same for electric fields that are directed along x axis or y axis or z axis or any other axis that you can think of. Okay. The value of epsilon r did not even change as we moved from one point to another point inside the material medium. Finally, we assumed that the electric fields of the light waves that are propagating inside the medium was actually not very highly intense, so that one could neglect the so called nonlinear effects. So, the first property whereby the permittivity or permeability would not depend on the direction of the electric fields or the direction of propagation, or its value would be the same at all directions, is what we call as the medium which exhibits this property is what we call as a isotropic medium. Okay. In the isotropic medium, the value of epsilon was a constant independent of whatever the direction of the propagation. The second property was the homogeneous property, in which the permittivity and the permeability did not change as you move from one point to another point inside the material medium. In this module, we will look at a special class of material media which we call as anisotropic materials. In fact, you would find lot of these anisotropic materials in optics and microwave applications. For example, you might have all observed the kind of a glass box or a crystal kind of a thing, wherein you send light in one and then you actually see double refraction, right. So, this phenomenon of double refraction is actually because the material that exhibits this double refraction is an anisotropic medium. In the anisotropic medium, the value of permittivity will depend. This is a dielectric anisotropic medium that we are talking about. Therefore, the value of permittivity does depend on the direction of the electric field or the polarization of the propagating light wave. Okay. How do we describe this anisotropic medium? It turns out that the so called scalar value epsilon r that we used is not really suitable for description of an anisotropic medium, clearly because you would want to say that if the electric field is along the x axis, what is the permittivity that this material sees, if electric field is along the y axis, what permittivity does it see, and so on. Okay. In general, it turns out that permittivity becomes what is called as a tensor, okay, and we choose to represent this tensor in the form of a matrix, or we give the elements of this tensor in the form of a matrix, and it is usually given by the value of epsilon naught, which is of course the constant that should go to everything, and in general this would be of this nature. So, you will have epsilon xx, xy, epsilon xz. Similarly, this will be epsilon yx, epsilon yy, epsilon yz. Last row will be epsilon zx, epsilon zy, and epsilon zz. Okay. So, what is this additional epsilon xx, xy, epsilon xz? What do they do is that if you have an electric field which has a component of Ex as well as the component of Ey, then these two components get mixed up between each other because of the non-zero values of epsilon xy and epsilon yx. Okay. So, we will see this. Okay. Now, in general, as I said, there are about 9 elements which are to be specified for an anisotropic material, but thanks to certain thermodynamic properties of the materials, this epsilon tensor, okay, is actually symmetric. If we assume that we are working with real time functions such as cosine omega t minus kz or something like that, then you can think of this as a simple symmetry relationship. But if you want to use the phasor notation, then you will have to look at, because the elements can become complex, but they will always be conjugate symmetric. Okay. So, whether you are working with cosine omega t or the phasor determines whether it is just a simple symmetric epsilon matrix or a conjugate symmetric epsilon matrix. Okay. Whatever that symmetry may be, linear algebra tells us that this type of a matrix can actually be diagonalized, okay, by a transformation known as similarity transformation. You can change a matrix which is full, it has all these 9 elements, but these 9 elements are in such a way that this matrix is symmetric or conjugate symmetric. Then you can diagonalize this matrix so as to obtain a completely diagonal, okay, permittivity matrix. Okay. So, you have epsilon x, epsilon y, epsilon z, where these epsilon x, y and z are not the same as epsilon xx, yy and zz. Okay. I will not go into details of similarity transformation. You can look up this similarity transformation in a more detailed manner in any of the linear algebra courses or textbook, but suffice to say that in general, when you have a full matrix which is symmetric or conjugate symmetric, then you can apply this similarity transformation to transform the matrix into a diagonal matrix. We will assume that we are going to work with this diagonal matrix and then see what happens as the wave actually propagates through this one. Okay. Now, one of the first things that you should recognize is that in general all these values on the diagonal, all the values of epsilon x, epsilon y and epsilon z can be different. Okay. Suppose they are not different, then suppose they are all different, then you actually obtain what is called as a biaxial medium, and because most of these media are made out of crystals, then it is normal to call them as biaxial crystals. Okay. Biaxial crystals means that there are two axes, okay, for every given direction of propagation. For a plane wave there are two axes over which E, D, H and B, all these vectors satisfy a particular relationship. Okay. In biaxial crystals you have epsilon x not equal to epsilon y, which is further not equal to epsilon z, but in a uniaxial crystal, which is more commonly used and which is what we are going to consider, for example a calcite or gallium arsenide, these crystals actually are what is called as uniaxial crystals. So, where epsilon x is equal to epsilon y, or rather epsilon x is not equal to epsilon y, but let us say this is equal to epsilon z, that is 2 out of those 3 values are actually equal to each other. Okay. And these epsilon x, epsilon y, epsilon z are all the relative permittivities that we are talking about. Okay. Now, we assume that we are given an infinite media, okay, and in this infinite media we describe epsilon by the tensor property, which we will assume that to be a diagonal matrix. So, you have a diagonal matrix with this epsilon tensor. Okay. Now, if I assume that all the field quantities E, B, H and D are propagating along the z direction. So, I will assume that there is a certain z direction that is determined by this one, and along the z direction, let us say the propagation of the fields are governed by the phase relationship of e to the power minus j beta z. Okay. So, you have all the field quantities going as e power minus j beta z, then what it means is that you can replace in Maxwell's equation the operator del by minus j beta, okay, or rather the vector minus j beta, where the vector beta is actually given by the value of beta itself, the magnitude times the unit vector along z direction. So, you have you can actually represent these operators, del operators, replace the del operators by this vector which is minus j times beta. Okay. What does that do? What it does for us is that you can simplify Maxwell's equation. So, you have del cross E equals minus j omega mu h, right. This equation will now become minus j beta cross E is equal to minus j omega mu h. Okay. You can remove this minus j from both sides, and then you see that beta cross E, right, the vector beta, the cross product of vector beta and the electric field E, which we will assume it to be a constant electric field E, to be equal to or to be proportional to the magnetic field H. Okay. So clearly H should lie in the plane which is perpendicular to the plane that contains both beta and E, right. So H is actually perpendicular to both beta vector as well as the electric field vector. So let us put down that beta and electric field vectors, to both of them H is perpendicular to each other. Okay. I mean H is perpendicular to both components. Let us look at the second Maxwell's equation. So I have del cross H is equal to j omega d. I purposefully did not write this as epsilon E because we no longer have a scalar value of epsilon to say that d and E are parallel to each other. In fact, d and E are not parallel to each other, okay, because you see d is related to E in the form of a tensor now. Okay, suppose just for our this one we will write this, consider the uniaxial crystal with 1.5, 1.4 and 1.4. okay. So all the other values are actually equal to 0. These are not the actual values, I am just showing it for the illustration purposes, and I have electric field E having an equal amplitude of along x, y and z, which therefore will have E0, E0 and E0. okay. So this is the electric field that I am supplying. Now what will happen to the D field? D will be say D0x d, or rather we just write this as dx, dy and dz, and you can clearly see that this dx, dy and dz, which forms the components of the D vector, will not be a parallel vector or some kind of a proportional vector to the electric field E, correct. You can easily see that because two of the components, that is y and the z components, are adding in the equal proportion, but E0 is not adding in the same proportion as the other. So you can't take one value or one particular number as a common factor to show that D and E are parallel to each other, as it would have been the case if you were considering a isotropic media. Okay. So D is not parallel to E, therefore I do not want to write j omega epsilon times E, where epsilon is a constant, but I can always write this D as epsilon times E. Okay. Therefore the second Maxwell equation actually becomes, by replacing del by minus j beta, then we actually obtain minus j beta cross H equal to j omega d, or equal to j omega epsilon times E. Okay. Clearly D is not parallel to E is a major departing factor compared to a simple isotropic propagation. Okay. Removing j from both sides, you can, and also interchanging the minus and signs for the cross product, you will actually see that H cross beta should be proportional to D, right. What does this mean? This means that beta is perpendicular to D, right. Beta is also perpendicular to H. So you have beta, D and H forming three different axes. So you actually have a right hand rule kind of a thing, where beta points along the x axis, let us say, and or beta propagates points along the z axis, then H propagate or points along the y axis, then D could point along the plus x direction, or D could point along the minus x direction. Whether you are looking at that, I mean both values are equally acceptable because the equations do not really distinguish which one or which one, but the important point is that you have D vector here, this is your this is the beta vector and this is the H vector, but the electric field vector is not along the D vector, it is actually at a certain angle with respect to each other, and this angle can actually be calculated by taking the dot product of D with respect to E. Okay. So you see that D and E are in the same plane, but they are not parallel. D and beta are in the same plane, but they are not parallel, but they are perpendicular. E and this one are also not in the same plane, right. So you actually have a triad which tells you that beta, H and D are the true three mutually perpendicular vector kind of a situation. Okay. They can be considered as the equivalent x, y and z for you, okay, in the anisotropic media. Okay. What are the other Maxwell's equations that we have? Well, we have del dot D equal to 0, which simply means that beta dot H, beta dot D must be equal to 0, right. So beta dot D must be equal to 0. This is the other equation that would tell you that beta and D are perpendicular to each other, and for us del dot B was anyway equal to 0, which means that beta is not only perpendicular to H, but beta is also perpendicular to B vector. There is no surprise here because B is actually parallel to H. Okay. So, in a given plane, right, you might have H and B, both of course are parallel to each other. Then you have a beta, which is the direction in which the wave is propagating, and you will have two solutions for D. One solution is for D in this way, the other solution for D would be in the opposite way, right. So, you will have another D maybe at this particular thing. So, you will have not exactly like this, but appropriately in the axis you can think of. I am not very good at drawing these vectors properly. D and beta are perpendicular, both are perpendicular to H. S would not be perpendicular, so S would be lying somewhere in the same plane. This is the electric field E. E would not be perpendicular, so E would be lying in this one. And other crucial thing is that your so called Poynting vector S, right, because Poynting vector is equal to E cross H, and E and D are not perpendicular, E and beta are not perpendicular. The Poynting vector S is not parallel to beta, but is actually at a certain angle to beta. But all these vectors, okay, all these vectors actually lie in the same plane. If you are having difficulty to remember what they are, you can remember this as the Dex plane, where instead of writing beta I have written K. Okay. So, otherwise it would have been Deb's plane, so it would not rhyme very nicely, but you can think of this as a Dex plane, saying that D, E are in the same plane, K is in the same plane, which is the propagation direction beta, and S, which is the Poynting vector, all lie in the same plane and all of them are perpendicular to both H and beta. Okay. So, this is what I wanted to talk to you about physically what is happening. Now, let us put down and ask ourselves, in the infinite media, anisotropic media that we considered, if beta is along the z axis, so if beta is actually the propagation direction of the wave is along the z axis, then what will happen to the corresponding value of beta? How do I actually find out what value of beta to use? Okay. And if I have value of beta to use, what would that impact on the electric field components? What would be the D field components? What are the possible solutions for the plane wave that is propagating in a anisotropic medium with this one? I can obtain this by going back to Maxwell's equation. So, I have beta cross E, right, equal to minus, or rather sorry, plus omega mu H. Okay. If I now take another cross product of with respect to beta on, or with beta on both sides, so I obtain omega mu beta cross H. Using the two Maxwell's equations for beta cross H, I can substitute for the correct value here. I mean, I can substitute for the value of minus omega D here, and beta cross E can be simplified using the A cross B cross C formula. I leave all those things for a small exercise. Okay. On the right hand side, of course, you will get minus omega square mu into D, and for the left hand side, substitute beta equal to z hat beta, sorry, this is vector beta and then the scalar magnitude of beta itself. So, if you substitute for z in this particular case, you will actually end up having minus x hat beta z square, or beta, I am just using this beta z here instead of just beta. So, just a small minor change in the notation. So, the propagation I am showing that it is actually with a subscript z. Okay. So, this would be minus x beta square E x minus y hat beta z square E y, which would then be equal to minus omega square mu epsilon 0. Now, you write down the complete tensor over here and then write E x, E y and E z. Of course, your tensor is only diagonal, all the other non-zero values, I mean all the other non-diagonal elements are at 0, right. So, you can write down and simplify the matrix to obtain minus beta z square plus omega square mu naught epsilon x. Okay. Then you have 0 and 0, then you have 0 here, you have minus beta z square plus omega square mu naught epsilon y, which is the y directed thing, again a 0 there. So, maybe we will put it in a proper matrix kind of a thing. So, you have 0 0, and because we took the value of y and z to be the same value of epsilon, and because beta is actually along the z direction, so you don't actually get any beta term over here, you will simply get omega square mu naught epsilon y. So I suggest that you actually work out and show that this is the correct matrix times Ex, Ey, Ez. This entire thing must then be equal to the 0 vector on the right hand side. Okay. This is a simultaneous equation, 3 simultaneous equations if you think of. The only way you will have non-zero values of Ex, Ey and Ez, this is a non-trivial solution, is when the determinant of this particular matrix actually goes to 0. And you can actually observe here, one additional thing that you can observe here is that because omega square mu 0 epsilon y times Ez, it will turn out to be equal to 0, and because none of these quantities can actually be equal to 0 unless you take omega equal to 0, in which case there is no point in doing all this. Okay. So it will simply tell you that Ez has to be 0. The only non-zero terms that we are looking for is for Ex and Ey. This actually makes sense because we considered a plane wave, and a plane wave should not have a component of E along the z direction, where z is the direction of the propagation. And then you have two conditions, either beta z square is equal to omega square mu naught epsilon 0 epsilon x, this is one condition, or you have another condition which tells you that beta z square is equal to omega square mu naught epsilon y. Okay. When one of the conditions is true, right, so when one of the conditions is true, then you can find out what will happen to the components of Ex and Ey. Okay. Or going back to the case that the determinant of this matrix has to be equal to 0 will allow us to find out what should be the value of beta. Okay. Again, if you can put that one down, you will actually come down with these two conditions. Okay. So in one condition you have beta z square equal to omega square mu naught epsilon naught. I can write this omega square mu naught epsilon naught as the free space propagation constant k0 square, and because epsilon is the relative dielectric permittivity is actually square of the refractive index, I can write this as nx square. Similarly, I can write omega square mu naught epsilon naught as k0 square, ny or epsilon y can be written as ny square. Okay. So if you put in these conditions, so if you force the condition 1, right, so if you force the first condition that beta z square is equal to k0 square nx square, then you can actually have Ex to be non-zero. So this actually implies that Ex is not 0, whereas Ey will be equal to 0. And what will happen to Ex? How does that propagate? Well, in that case Ex can be assumed to be some constant Ex0 with a propagation of minus j beta z. Let us put down a 1 here just to indicate that this is the propagation constant for condition 1, where beta z is actually equal to k0 nx. Okay. So in that condition Ex will be non-zero with some constant value of Ex0, which is the plane wave constant that we have taken. Ey will be equal to 0 and Ez is also equal to 0. I will also write down the values of dx. You can show that this would be true. This would be equal to epsilon 0 epsilon x, okay, times Ex. In this case you can see that dx will be parallel to Ex, right. So provided that you have only Ex component propagating inside with beta z taken as the condition for beta z1, dx and dx will be parallel to each other. It is only when both components Ex and Ey are propagating, then d and e will be not parallel with respect to each other, right. And you can also find out what will happen to h will be along the y direction, and this would be equal to some Ex by eta 1, where eta 1 is determined by the ratio of beta z1 to omega epsilon. This particular wave is called usually as O wave or the ordinary wave. Okay. You can put in the condition 2, and in the condition 2 what we have is that beta z should actually become beta z2 given by k0 square ny square, okay, or rather square root of this one. So sorry about that. So this should be k0 into ny. Okay. And you can then show that Ex will be 0, Ez anyway is 0, but it is Ey which is not 0. Okay. Ey will be some constant Ey0 e power minus j beta z2 times z. Okay. And you can clearly see that beta z1 can be either greater or can be less than beta z2 depending on whether nx is greater or it is less than ny, right. Suppose nx is greater than ny, suppose this is the condition that we already know for some way that nx is actually greater than ny, then what will happen, because the speed, the phase velocity is inversely proportional to x, right, the phase velocity of this fellow will be less than the phase velocity of y. And we have already discussed, whenever two waves of same frequency propagate through a medium with different phase velocities, there will be a phase difference between the two. And what will be the effect of this phase difference, which actually depends on the propagation distance as well? The effect is that the polarization, initially you might have started off with a linear polarization, let us say at 45 degrees, but then as both components travel, 45 degree can be decomposed into Ex and Ey. As Ex propagates with beta z1, Ey propagates with beta z2, eventually they will propagate with a velocity or with a total phase angle change of beta z1 minus beta z2 into whatever the length of this one, right. So, whatever the length of propagation of z. Okay. What actually happens when this condition is satisfied, that both waves travel, the O wave, and incidentally this wave is called as the extraordinary wave. So, this wave is called as the extraordinary wave or E wave. So, what happens is that O wave and E wave will interfere with each other at different, will superimpose with each other with a certain phase difference, which will in turn translate into a polarization rotation. Okay. In fact, you can start off with a linear polarization along x, and at the output of the crystal or output of the uniaxial material obtain a circular polarization. In fact, this is one of the primary ways in which polarization in optics is manipulated. You actually start with a linear polarization, and if you want to convert it into a circular polarization or circular to linear, you can do all sort of polarization conversion. You can do so by employing these crystals, which internally take up the light that is incident on it, break it up into two parts. One part will be O wave, the other part will be E wave, and when they put them back together at the crystal output, you see that the polarization is not the same as the input. So, this polarization rotation is an extremely important thing. Okay. So, this completes our discussion, extremely brief discussion of propagation of waves inside a anisotropic media. Thank you very much.